including a full range of RF Elements antennas. RF Elements are focused on product innovation, which has resulted in some really exciting and well-made pieces of kit. They've got a great CEO in JT, and they know exactly what they represent as an organisation. We're lucky to have Michael Mardiak, who's the product manager for RF Elements, with us, and he's going to talk to us about noise rejection. So all that remains to say is that there will be a Q&A session at the end. Please keep your questions until then, and now it's time to hand over to Mike. Enjoy the session.
Thanks MS Distribution for doing this webinar. My name is Michal Mardiak. I'm the product manager here. So again, this webinar is we are making it together with MS Distribution, and this is live webinar. So first of all of you are muted. So if you have any question, please use a GoToWebinar tool. There is a question window, so type their question anytime during the webinar. And at the end of the webinar, I will answer the questions. So let's start with the webinar. So today's webinar will be about technology for fast sustainable wireless, especially for noise rejection one-on-one. So first part of the webinar will be about our technology, the key feature, and how it helps you to solve the current problems that we have. And the second part will be about the best practices for deploying wireless network. And I would like to share our vision how the network should be deployed. We will also have some section about the Mythbusters, so let's say a typical specs base on which you typically buy the antenna and how these specs are transformed in a real life deployment. So the technology for fast sustainable wireless. So this technology is basically in all our new antennas, which are based on horn technology. And it's really interesting technology because it allows you to grow smart and reject the noise, so you can utilize the spectrum as much as you can. So as I said, you can utilize the spectrum. So today key challenge is really the spectrum. So we all know that because the noise floor is really climbing day after day, and we only have a finite fixed amount of spectrum. And also in the spectrum that we currently have, we are fighting with restriction, many restrictions like out of band emission, power levels, DFS, you name it. There is a lot of those challenges. So really the ability to use and maximize the spectrum is the key for growing and dealing with the challenges that we have there. And hopefully with our technology, we can make you think about how you are deploying your networks now and how you could possibly deploy differently and using some methodologies there that are unconventional or something like our products. So among all of those challenges that we have in the spectrum, the main problem is really an RF pollution. So today antenna systems are using or the radio system that we are using for outdoor wireless are making an RF pollution problem really grow at exponential level. So the problem of RF pollution is mainly caused by almost endless amount of RF noise that is created by poorly designed and deployed gear. And basically noise could be categorized as any signal that is not intended for your target whenever you are generating it or not. So this noise usually is result of RF signal that travel way past of your coverage area further than we need it to be, and also in unwanted direction, so the direction that we do not expect to. So the noise that you are facing is not just the noise from other competing WISP, but it is also your own noise, so created by yourself. And really the RF noise and interferences are the biggest challenge for today's WISP. So these are the data that we collected in November 2016, where we asked in this survey what is the biggest challenge, and you can clearly see really the RF noise and interference is the biggest challenge or biggest issue for today WISP. So our technology deliver fast, massive scalable wireless while addressing the issues of RF pollution and proper use of the spectrum and sustainable growth. So we have these three key principles to achieving that. One of them is the noise rejection. So all our antenna based on scalar technology, the scalar horn technology, are coming with this technology, and we focus to create antenna that reject noise by having suppressed or no side lobes at all. Another principle is a zero loss system. We call it a Twistport connector. So it's really, if you use an adapter, it's really virtually without loss. And also thanks to these two key principles, you can scale your network massively. So the only way how to cover increasing demand for the internet is basically deploying the networks differently. So growing smart, rejecting noise, and save the spectrum. So let's have a look at these principles in more detail. So the noise rejection really is one of the main benefits of our antennas. So if we look closer into this principle, we have two different antennas pattern here. One is the mainstream traditional antenna, and another one is our horn antenna. So on the left side, you have a typical patch panel antenna. This one is roughly 120 degrees. But from the RF point of view, you really don't get that. These antennas really have a huge and very complex side lobes. And if we look at the side lobe size proportion, side lobes are really large. And these side lobes are not only huge noise generators, but also a huge receptor of noise. So with such a huge side lobes, really the RF planning is very difficult. So side lobes are sometimes stronger than you would think. And this is really an issue when you are trying to do the collocation or channel reuse, and not just on your tower, but also on neighboring towers. So our approach to the problem of RF pollution is very simple, but also very unique. So instead of dealing with the excessive amount of noise by using some kind of complex and expensive methods like active filtering, GPSing, TDMA, and so on, we really focus on correct signal propagation. So with our technology, the signal really purely goes only in direction that you intended for it to go. So no side lobe, just one main lobe. And this is for sectors antenna, but same happens, or maybe even worse happen in a point-to-point solution. So the huge side lobes for high gain antennas and also the parabolic dish antennas are really an issue. The side lobes are usually even bigger than with the sector antenna, because front gain of the point-to-point antenna is bigger compared to sector antenna. And what is even worse, you have the same antenna on the both ends of the link. So you would collect huge amount of the noise on both sides of the link. That's on the left side, but on the right side you can again see our horn antenna for a point-to-point link, and this is a highly directional point-to-point antenna with no side lobes and very precise beam. So signal purely goes only in the direction that you want it to go, and if the client, or the client on the other side, is outside the main beam, the signal drastically drops. So that was the first principle, the noise rejection. But there are two key issues when you are trying to achieve a superior wireless performance. So one is a noise rejection, I already spoke about that, but the second one is a RF loss. So let's speak now about the RF loss. So typically in your configuration you have three items, so the radio, antenna, and cables. So the cables, the signals from the radio travel through coaxial cables and connectors where the part of the signal is lost. And on average, you can see from about 2 maybe to as high as 3 dB loss just because of the cables. And that's not all. The cables also don't cause just the loss, but there is also a very high failure rate due to this cable. So you know that you need to have a proper configuration of the pigtails. It depends on who make it for you, whenever you have a right angle of connectors, if it is high or low quality, or if there is a loop on the cable. So really many things that can go wrong. Our proprietary Twistport connector is completely different. It's based on a waveguide, and it doesn't have any cables or coaxial components. It uses the waveguide to transport the RF signal between the radio and the antenna. And really, in comparison to current market standard, which are RP-SMA coaxial cables, Twistport is virtually lossless, and it's also extremely easy to use and very durable. And it's not just that the Twistport is eliminating the #1 source of the loss, so the pigtails, but it also eliminates #1 source of the failure, which are again pigtails. And the third key feature of our technology is massive scalability. So really, with the current wireless equipment, you are not able to achieve higher or increase your granularity in the network. So if you look on the left, you can clearly see how the side lobes of current industry standard do not allow you to do the collocation on your tower. So with our technology, you can now supply the increasing customer demands for connectivity very easily. You just deploy more sector with much higher density. And so this is how you can instantly multiply the performance on your tower, putting there more sectors. And really, this technology or this antenna really doesn't mean that our antenna allow you to, do the only thing that they allow you to do is the collocation on the tower and give you the opportunity to have a higher density of the sector per tower. But also, these antenna allow you first time to do the proper RF planning of your network, because with our horn antenna, you can, for the first time, really know where the signal is going and stopping the signal to going to the places where you don't want to have it. So with our antenna, you have the ability not to only collocate with great isolation on the tower, but also to plan the frequencies. And horn antenna give you the variety and the flexibility to scale your network as you need and deliver the promised service to your customers, and just to your customers, not anywhere else. So now let's move into the deeper dive in RF planning, and I would like to show you how the technology that you are using today really working compared to how you might think it is, and also compared to our saving spectrum technology. So really think about being efficient with our finite resource, which is spectrum. So nowadays, let's say there are 3 typical types of the sector antenna that we usually speak about. So you can see them here, their 3D antenna pattern. So on the left side, there is an OMNI antenna, which is really simple. In the center, we have a traditional sector. So traditional sector has a very flat vertical beam performance and usually very wide horizontal beam. So usually you have either 120 degrees or 90 degrees or 60 or even 45 degrees, but what you can see here are really big side lobes. So not only on the back, but also on the top and the bottom. And these side lobes are counterproductive for many reasons. So the main one is interference receptions and connectivity. So the connection on this side lobe is really very ineffective, and a poor way of connecting your client. So it might work in some certain situation, but typically intensity of the side lobe is so tight and high that client might have a good quality of signal, which might give you the illusion of good connectivity, but when it comes to the customer user experience and getting the bandwidth that you're supposed to deliver to them, usually customers are really don't see it and are not very happy. And on the right side, we have a symmetrical horn antenna. So this is a typically beam pattern for a horn antenna, and you see that it's really symmetrical. So the performance, the horn antenna has the same vertical and horizontal performance. And this is a typically beam pattern of the horn antenna, and there are no side lobes. So there is only one extremely small back lobe, but it's so small that there is basically nothing that the main beam connectivity. So if the clients are outside the main lobe, signal drastically drops, or even the clients which are outside the sector or the main lobe will not see the signal at all. And this is really great tool for you because you can be really sure that your clients are not connected to the side lobes and are connected just to the main lobe, and you don't need to go there and measure the signal and try the speeds there, because you know the customer is just in the main lobe if the customer has a signal. So let's start talking about the OMNI's antenna, right? So to OMNI or not to OMNI. So the OMNI antenna works well for really short distances or for some kind of a hotspot or small micro pops, but in outdoor for a larger range it's really difficult to manage an OMNI antenna. So first, basically, because there is no RF planning, because you are sending the signal all around you whenever you have a customer there or not. So, and it's also one point of failure for your network, which is typically not a good idea. So, of course, I have to admit here, of course, there might be some, let's say, not really dense area where you have to cover fairly large range and you don't have enough customer to justify the sectoring the tower. But all we try to say here is just look at the area that you have to serve. So if you look at the places where you really have customers, maybe it is enough to do the point-to-point connection, and it might be really a better solution. So look at the coverage that you really need to cover. And here is the example. So in the pictures or on the pictures, the installation, you have 5 clients, so point-to-point CPs. So if you cover it with the OMNI antenna, you really will cover a 360 degree, but you need in reality you need a cumulative coverage around 100 degree in order to serve them. So if you do the point-to-point rather than OMNIs, you will save roughly 260 degree of broadcasting information. So those information that you really don't need, and this is what will increase or will have a bad impact on the noise floor. Now let's look at the traditional sector versus horn coverage. So on the left-hand side, you can see an example of a traditional sector antenna installation. So the red pins on the picture, the red pin is the tower, and the yellow pins represent the clients. So looking at this, you might think that putting 2 120 degree sectors will be enough and will not transmit the signal on the backside behind the tower, but that's not the way how the antenna works. So you can clearly see that you are transmitting behind the tower as well as on the sides. But not only that, but you are also sending the signal way past your coverage area, beyond the area where you have customers. So you can turn the output power down, but you can't change the gain of the antenna. So due to this, you are giving too much receiving power to your AP. And now if you look on the right side, that is what the horn antenna will give you. So on the bottom side of the coverage, you have a, let's say, high density sector. So it's really hard to stack a multiple traditional sector about to coverage the same area. And I'm not speaking just about their side lobes, but with the horn antenna, you can split that 90-degree sector into 3 30-degree sectors, which will give you 3 times higher density, meaning 3 times more APs, meaning 3 times higher throughput per tower. So the customers on the same picture, the customers on the right side are not that far from the tower and are concentrated on one area. So horn will give you an ability to cover only your clients and not spreading the signal elsewhere. Also, here you don't need to have a high gain antenna, and even the antenna with the lower gain is enough. And it will also allow you, I mean, if you use a lower gain antenna, you will also hear much less from the other antennas. And on the right, there are the clients, for example, in the mountain. So with usually flat beam of the traditional sector antenna, you really can't connect these clients. You need a huge vertical beam, so the beam that horn antennas offer. So the fixed gain is really high fixed receiver gain. So something that you really can't control or adjust. So make sure that your clients are hearing the AP and try to use the antenna with the lowest gain that you can, because this will also help you to utilize the existing spectrum. So you will not creating noise. And also the proper transmitting power and receiving gain is very important. And here you have a traditional sector antenna with a fixed 20 dBi gain, and on the other side you have a lower gain horn antenna. So when we look at the typically radiation pattern, we usually think of them in one way. So only the measured gain of the main lobe in relation to your CP distance. So that's the green color. But again, what we usually ignore is the distance that your AP signal will travel past your coverage area and then becomes noise to your radio as well as to the other. And that's the red area. Here I have to say that the scale that you see there is really a real life scale. So it's really a huge distance that the antenna is sending the signal. So what people usually do is they just increase the transmitting power with these high gain antennas, and this is really happening that they also reduce the available spectrum and create more and more noise. And you can see when we compare them, so the traditional sector antenna 20 dBi with our 10 dBi and 10 dBi symmetrical horn antenna, you can clearly see that both antennas are able to achieve similar distances just with tuning or putting up more takes power on the horn, but drastically reduce the noise that you will receive and create as well. So the difference between this antenna is really very, very clear. So this area that is blinking, those areas are the areas from where you are receiving the noise and you really don't need it. So in conclusion, more forward gain antenna is not always the answer. So high gain antennas create more problems with side lobes, and also it may those antennas make it harder for you to manage your available spectrum. When we talk about the needed gain versus distance, I would like to point out a few things here. So currently on the market, many WISPs are using the appropriate CP based on the distance on the tower. So if you have your tower, let's say 3 miles or less, typically you are using something like a PowerBeam 16 or PowerBeam 19, so basically some CP that are roughly 16 dBi gain antenna. So if you coverage area between 3 to 5 miles, you will go probably with a PowerBridge 21 or PowerBeam 300, so around 21 dBi gain CP. So if you go beyond that, 5 to 7 miles, there is a CP like a PowerBeam 400 or PowerBridge 25, and beyond 10 miles, some people are using rocket dishes or higher gain antennas. But when we look on what we are doing on the AP side, that's something else. You have the sector gain. If you have a customer no more than 3 miles away, you're still using typically high gain sector antenna, let's say in average 20 dBi. 3 to 5 miles, same. 5 to 7 miles, same. So really, we are not using a lower gain sectors for closer distances, or we don't usually lower the output power. Most people are using full output power because everybody is trying to talk over the noise. But when you are deploying your CPs, you are using a proper gain based on the distance. But when you are deploying your APs, that's not really happening. So with our antennas, you have an ability to tune your network to get better performance by using antennas with appropriate gain on your AP side based on the distances and really the area that you need to cover. So we are really giving you the options and to really to build your network as they should be, and to plan your network and frequencies as they should be. So based on your customers, where they are located. So at the beginning, I said that we'll also have a short section about the myth busters in antenna aspect. So probably most of you already know this, but this is about the products that are out there and how they work. So we often have a feedback from customers saying that basically the gain of our antenna is too low. So they are currently using a 20 or 22 dBi titanium sector, and they are having a hard time to connect clients 5 miles away. So how could we say that you are going to perform better with our 18 dBi gain horn antenna, right? It doesn't make much sense, because they expect like 2 to 3 dBi less signal than they typically getting. But the first thing that I have to mention here is that usually those gains are the maximum gains. So it means that the maximum gain is only on a specific frequency and just on one polarization. So if you look at the graph on your left side, you can see a mainstream traditional sector antenna gain for both polarizations, so the horizontal and vertical one. And you can see that the gain in a horizontal polarization is roughly 18 dBi, and in a vertical is no more than 15, and somehow manufacturer come with an average gain of 19 dBi. So it's completely different with our symmetrical horn antenna. The gain is practically flat around the frequency spectrum. But what is also very important, the gain of the symmetrical horn antenna is same for a horizontal and a vertical polarization. So you don't see much deviation in the frequency range, and the horizontal and vertical performance is identical and this is very important in MIMO deployments when you really want to have your chains well balanced in order to achieve a higher modulation rates and really balance performance. So sometimes people see with this with those mainstream sector antennas a 5 dB difference between chains, what really is killing the modulation rate and increasing the error rates and significantly degrades the throughput. But this is not the case if you use symmetrical horn antennas. Next thing that I would like to talk about is MIF and the beam width in the beam width in antenna specs. So the beam width at the -3, -6 and -12. So -6 is a new industry so-called standard that was invented by UBNT, but most of WISP know that they are looking for, most WISP know that, so the WISP usually are looking for a -3 beam angle. So how to read these -3 and -6 values? So if you look on the patch panel antenna, let's say it's a 20 dBi sector. So at -3, it is 90 degree and the signal toward the edge drops about 3 dB. And at the end of that 90 degree, it's no longer 20 dBi sector, but it's really a 17 dBi sector. So if you go to -6, the gain is roughly 14 dBi. So at the edge of 120 degree sector, it's not a 20 dBi gain sector anymore, it's just 14 dBi. And at -12, the sector is over 120 degree, but just around 8 dBi. So if you look at our symmetrical horn antennas, we still follow the same logic from -3 to -12, but you can clearly see how close and how fast the signal drops off. So if you buy the sector on the left, thinking that you are having a 90 degree sector, you put 4 of them on the same tower and think that you hear just those 90 degrees. But here you can clearly see that you still have extremely high sector performance beyond those 90 degree. So you are sending the signal beyond the area where you want to have it and really creating the collocation issues for you and making it hard for you to reuse the channel on that tower. But with the symmetrical horn antenna, you will have a precise radiation angle and the signals really rapidly drops outside the main lobe, so you will not spread signal everywhere around. So that's why the collocation and also frequency reuse or channel reuse with the symmetrical horn antenna is really very easy. And last thing I would like to mention here is front to back ratio. So this is probably one of the most important metric for people who are going to buy the antenna. I mean, other than the front gain of the antenna, which they used to, let's say, try to talk over the noise floor. So front to back ratio, so people really often think that front to back ratio is something that will help them to collocate on the tower. But it's not the whole truth. And I would like to show you why. So in order to do that, let's have a look how the front to back ratio is calculated and measured and how much of the antenna pattern is not included in the front to back ratio parameter. So if you look at these two antennas, front to back ratio is pretty simple to calculate. So it is a ratio of the forward gain of the main beam measured in dB and the gain of the back lobe also measured in dB. So both of these antennas, based on their specs, have the same front to back ratio because the intensity of the back lobe Y here in dB is the same for both antennas. So this is what specs are telling you. But what the mainstream manufacturers aren't mentioning or showing to you in the data sheets or wherever it is the intensity of the huge side lobes and back lobes that the antenna has. So when you are buying the antenna purely based on the front to back ratio, you are considering the antenna just based on this mathematical equation, so the straight line from the center of the main beam down to the back side of the antenna. So on the paper it looks the same, but in a real life deployment you will have completely different performance. So you should now really care about the front to back ratio as much as the huge side lobes, which are creating noise, and also you are receiving the noise from those side lobes. So those side lobes are giving you a hard time to collocate. So, and here it is. If you overlay both antenna patterns, you can clearly see a huge difference there. Different side lobes, different noise isolation, and much different collocation ability. So again, same front to back ratio, but completely different antennas. So front to back ratio is not the only thing that you should look for. You really need to know the whole antenna pattern, how it looks like, in order to be sure how the antenna will work. So I was speaking about the symmetrical horn, so now I would like to briefly show you what kind of models do we have and what you can connect to this antenna, because as I mentioned, the antennas come with the Twistport connector. So this is very briefly few parameters here. We have 7 different models, starting from 30° up to 90° with 10° step. So really you can pick exactly the antenna with the radiation angle that you really need for your network. I was speaking about the Twistport connector, so it's our proprietary connector, but we are also giving an opportunity to connect a third-party radio. So really Twistport offer you great cross-platform compatibility. So in order to do that, you need to have a Twistport adapter. So adapter really works very simple. You just slide the radio in, and when you want to release it, you just press the button, remove the radio. For Ubiquiti radios, here are the Twistport adapters that we currently have. The AirFiber 5X will come this year. We also have a Twistport adapter for EPMP 1000, so from Cambium network, basically all mechanically identical EPMPs 1000 you can use with this Twistport adapter. And if you are using a Mikrotik route board, again there is a Twistport adapter. It's working slightly different than the others. Here you need to screw the route board inside, connect the pigtails, close it, and you are ready to go. So these are the Twistport adapters that we have, but we also have other types of the antenna, but well, types. These antennas are symmetrical horn antenna, but these antennas come with the N-type connector. So basically, if you have a radio and you don't have, or we don't have a Twistport adapter for you, we're still giving you an opportunity to use a symmetrical horn antenna. You will not have a benefit of the Twistport, but the performance of the antenna is similar to the Twistport one. And as you can see here, the antennas come with the N-type connector, so you can connect any radio. For example, Mimosa radio A5C, so 4-chain radios. Here I need to say that yes, the radio is 4 chains, the antenna is just 2 chains, so you have to use 2 antennas, but it will really give you an opportunity to plan the network and deploy the network as you really need, because you are flexible. If you want to cover one sector, you can use both antenna covering one sector. If you want to cover two different sectors, you can pick antennas based on the both sectors, connect it to the antenna, and it really works. We have amazing feedback on the sector carrier class antenna combination with Mimosa radio, so people really love them and it's really working. So that was about the products. A few more things to share with you here. We have our community. The community is called RFE Lab. You can go there, register for free. It's a user-based community, so if you have any question, I mean, later, or you would like to just check what's new or what are the problems or what are the questions from other users, go there. A lot of really useful information there, and you will learn definitely something interesting there. We are traveling on many different shows and events, and on those events we are trying to make some videos about our customers and their feedback. So if you would like to hear those feedbacks, you have to go to our YouTube channel and check there. A lot of customer feedbacks there. We basically ask them what was their problem in the network and how our antenna helps to solve them the problem. One thing I have to mention here, we also visited the guy which is in the down left corner, the Cosmos Wireless, and we did with them a video just about this WISP. It's the biggest WISP in Cyprus, covering whole country, so it's very interesting video. So again, it's on our YouTube channel. So we are also available on all of our social medias, the Facebook, Twitter, and so on. So we are publishing them a lot of interesting things. So if you want to be updated, just follow us or like us, and you will learn a lot of interesting things. As you can see, and it was already mentioned, this webinar we are making it with together with our UK distributor, MS Distribution. So these guys are really great and they have our product. So if you want to buy anything, just visit their webpage. So that was all from the webinar point of view, the presentation. Now I would like to answer the question. So first question, do RF elements have a PTP antenna to suit Mimosa B5C? Well, so for those who don't know, B5C is a point-to-point radio from Mimosa. It comes with the two N-type connectors. So for now, we don't have a solution with N-type connectors for a point-to-point. We will have a point-to-point antenna ultra horns that will come this year, but we are still not decided if we will have an option with N-type connector. So for now we don't have. So the only way how to use it is with a 30-degree symmetrical horn antenna. But again, the 30-degree horn antenna, the beam width is 30 at -6, so it might be a bit wider for the point-to-point solution. So another question, how do antennas with the metal backs emit and receive RF from behind, given that metal reflects RF? How do antenna with the metal backs emit? Okay, that's the same question twice. So I guess that you are referring to these symmetrical horn carrier class antennas. So really, you don't need to worry about the emitting of the signal on the backside. There is a small back lobe. So we have the front to back ratio in our data sheet. So if you download the data sheet, you can check the front to back ratio. So there is a small small back lobe, but otherwise really it's well shielded, so you don't need to worry about the side lobes and so on. Really, there aren't any side lobes. Do you have a link planning tool available for your antennas? That's also a great question. Unfortunately not, but yeah, we are making a lot of things here, so we are trying to provide with the best best tool or tools that can help you. So for now we don't have, but really if you are not sure how to plan the network, or you have some doubts about the product, so just visit rfvlab.com, ask the question there. A lot of people from our company, including myself, are present there, and we will definitely help you. Maybe we'll ask for more information, but at the end we will able to help you on, or advise you how to plan the network with these antennas. With with the A5C, as it's a quad antenna, can we use 240° to cover 80°? Exactly. That's the way how you can use it. Both of, the antennas are horizontal and vertical polarized, so again you can use it to cover two sectors. So just turn one on one side and turn the other sector and the horn antenna on the other side, and that's how you can cover the sector. And people are really using those antennas as that, and it's working very good. Will the A5C beamforming work using the horns? That's a good question. Well, the beamforming it's a feature of the radio. So it should work with the antenna when they are pointing the same sector. So that's it. Okay, we don't have any questions. So I'm really glad that you come to our webinar. Hope that you receive something, or you learn something new. There was a lot of plenty useful information. So really, I'm glad that you come. I would like to thank you, MS Distribution, for this webinar, that they invited us to make this happen, and I'm really looking forward to other webinar with MS Distribution. So this is all from my side. So guys, it's your turn.
Thanks very much, Mike, for that. There will be a video cast made available of today's session on our YouTube channel. And for those of you that are in the UK, we've also got an RF Elements Roadshow planned for the 22nd of February, which will happen in Banbury. We're especially excited about that, as that's the first time that we've worked with RF Elements on such an event. And I actually think that is the first time that they've run something like that in the UK as well. So it would be great if you could be there. We'll send out an email with more details about that tomorrow. I'd like to mention as well that the RF element horns, the horn antennas that we've been hearing about, they work really well with the Mimosa products. And Mimosa are running a promotion on C5s at the moment. If you buy 4 of those, you get 1 free. I understand that there are limited stocks on that, so if you are interested, get in there early. You'll find details about that on our website. And at the risk of sounding like I'm over-promoting, there was a question asked about planning tools for RF element antennas as well. Network planning support is available through our technical team here at MS Distribution UK Limited. So thanks again to Mike, and thank you all for taking part. Enjoy the rest of your day. Goodbye.